AI-based interpretations using the Gemini API. This will equip you with the real-world cardiac AI applications. So let me tell exactly what we're building today. Today we're building an AI-powered clinical analysis tool using the Gemini API, a real biosignal pipeline. So it's the same kind of architecture that's behind the Apple Watch detection and a lot of other products that have gone through the FDA clearance as medical devices. So the data we're using, it's real, and it's called the ECG heartbeat categorization dataset. It's free on Kaggle, and it contains 87K heartbeats from real patients. And they were annotated by cardiologists. So the data we're using is not made up, it's actual and from real people. And then we will load the data, visualize it, extract clinical features from it using signal processing. And then we will use the Gemini layer. We will use its model to reason those features and the same way a physician would. And the good thing here is that everything would be running on Google Colab. It's free and there's no installations or setup needed. So let's give some context to what we're doing. So what's an ECG exactly? It's an electrocardiogram. This is what it stands for. And basically it's voltage over time. So we all know that our heart is a muscle, and every time it contracts, it will generate a tiny electrical signal. We measure that signal by placing electrodes on the skin surface, and the result we get is a wave. So here's a representation of this wave. This is an almost perfect one. It's called the PUQRST complex. So each of these represent one complete heartbeat, and it has different locations. So let's start with the P wave. It's basically the top chambers contracting. So the top two chambers of the heart pushing blood down. And then we move on to the QRS complex. What happens here is we get a big spike in the middle. On an anatomy level, what happens here is the ventricles would contract, and it's basically the main pumping action. The R peak is the tallest point of that spike. Then we have the T wave, and it's the heart resting electrically and getting ready for the next wave, which starts from the P wave again. So now this is a normal beat. It looks clean and sharp and has a nice tall R peak. It's symmetric and it has a consistent width. But an abnormal beat would be, because we're going to look at the ventricular ectopic one. It's a heart disorder. So in these ones, what happens is it's more wider, it's irregular, and the peak is less sharp, and the shape is a bit disoriented. And we can see that difference really clearly with our eyes. So what we're adding today, it's an AI reasoning layer on top of what we can tell, and instead of just hard-coded rules, we will extract numbers from the signals using signal processing, and then we will hand those numbers to Gemini and ask it to reason about them. Here are just some facts about the dataset we're using. We will also only be focusing on the normal sinus rhythm and the ventricular ectopic. Basically, what this means is we will just have a normal version of the beat and a disordered one. Here's the dataset we're going to be working with today. And let's move on to the hands-on part. So let me just show you the finished product before we go into more in depth with this. So just tell me if you can see the screen of the collab.
Yes, we can.
Okay. So let's go to section 3 here. When you look at this, we have two real heartbeats. The green one on the left is a normal sinus rhythm, and both are from real patients, and the red one on the right is a ventricular ectopic beat from a different patient. From same data set, just different people and different labels. You can already see the difference without me explaining anything. The green one has a clean, sharp spike, the red one is wider, messier, and the peak is less defined. Those differences are what shape the diagnosis using an ECG. This is what you will get when you have an average of 200 beats from each class, the typical shape for each beat type. The differences become more obvious at scale. Normal beats are consistent and sharp. The ectopic ones are wider and irregular. So the main objective today, as I said, is we will have Gemini interpret those readings. And this is a final model of it. So here Gemini took these readings and it came up with three key things, basically a interpretation, a comparison of the values to the expected beat type, and one key limitation. So this is basically what it says about this, and this is the whole pipeline. Now let me show you exactly how this works. But first, I need you guys to open Google Colab so you can follow with me and work hands-on with this. I think it should be in the chat. Just give me a thumbs up when you have that open. Okay, so first here is what we're gonna be. Yes, Amir?
Sorry, by mistake.
Okay. Yeah. So first of all, we have the first section where we set up our code. We will have a install cell basically. Here we're just gonna download the libraries and everything, but what we really have to download is just the generative AI library. The rest is already embedded into Colab, like Pandas and NumPy and Matplot library. Then we will just, here we import them, and then the most important part of the day is it's getting the API key and putting it in your code. So I think our team have pasted the AI Google Studio link in the chat. Please open it and follow with me so you can get the API key. So when you open AI Studio, you will be faced with this page. Just go to Get API Key and then create API key. Here you can create a project and then press on create key. You will get an API key. Just paste that into the Kaggle, but into the Colab, sorry. But what we're going to do here today, it's because API keys are they have to be secure. We're going to use it as a secret. So you will press on this icon here, and then just in the name it as Gemini API key and the same spelling as this, and then paste your API key here. All you have to do then is just labeling it as API key, and then adding this function and just pasting the name you set for the API key here. That's all you have to do for that part. Just let me know if that's clear because it's the building block for your whole code. So just give me a thumbs up if it's all good. Okay, great. So just going back to this, what we did here is we pasted the API key, and this is going to authenticate us to the Google servers because we're using their model to run everything. So here we're just specifying the model and then just giving ourselves a little message that tells us that everything's working. So you just have to run each block and you should get something like, depending on what you set it here, that tells you that the pipeline is ready. Then moving on to section 2, this is where we bring in the data. Again, my team has sent you the data set that we're going to be using now, and just download that and import it into your Google Drive. Don't put it into any folder, so you can be able to just copy what I wrote and it will work fine. It should work fine. The thing is, we can't really just import it here because it's a big file, so we'll have to mount it from Google Drive. Again, just give me a thumbs up if you have downloaded it from the chat. Okay, great. So what happens here is we will load the data. So this is where we bring in the data set. It's just 2 lines of pandas where we will mount the file from Google Drive. It will connect your Google Drive into the Colab environment, and you will have to authenticate that. Basically, it's just gonna give it an access to your drive, and the CSV file, as I said, it's too big, so that's why we have to do that to this. We will read it using pandas, as you can see here. It's a function that reads CSV files into a data frame. Think of it as a table. Basically, even if you open the CSV file, you'll just find a bunch of columns with numbers. And then we will pass header equals none because this CSV file has no column names, and we will have to do them ourselves, as we are doing over here. So basically what this line generates is we will have the first 187 columns as T0, T1, T2, all the way to T186. And what these represent is the signal samples for each beat. So the 188th column gets named labeled, and that's the class 0 for normal, and for the ventricular one, it's going to be 1. And then we have 3 for fusion and 4 for unclassifiable. Yeah, and then here basically it will read the file. We have almost 72K normal beats and almost 6K ventricular beats. Here we're going to extract one example of each type so we can be able to represent that. Then moving on to the visualization step, we will define the single columns and the time axis, and then pull out one example from each beat class, which is what I just showed you a bit ago. We pulled two examples from each type, and then we plot them side by side. So the second plot in this section is the average of 200 beats per class, and we're using iLog to grab the first 200 rows from each class. So again, from each class, the data frame, we're calling it dot mean axis equals 0, averaging down the columns to get the typical shape, which is what happens here. Basically, what this means is we're scaling them so there are more, you can visualize them more. Now, when it gets really interesting, it's section 4. We are extracting futures. So what this means is basically we're signal processing here, and we will define a function called extract futures over here. It will take a beat signal and calculate 5 things. These 5 things are what usually clinically they rely on to diagnose an ECG reading. So we have the R peak over here, which is, like I explained, the tallest peak in the graph. We will find the index of the tallest point in the signal, and that's the R peak. The amplitude is just the value at that point, basically a reading of it. Then we have the QRS width. We will define a threshold at 50% of the peak amplitude and count how many samples are above it. We will convert that count into milliseconds, and it will give us the width of the main spike, because we really care about the width here in the QRS part, because it really tells us, because that's the main difference between the normal and abnormal. In the normal, it will be narrower, and the abnormal, it will be wider. Then we have the rest time. We will find the signal when it crosses 10% of the peak, and when it crosses 90% of the peak. And we will measure the time between those 2 points and see how quickly the signal rises to its maximum. And then we have the signal energy and baseline. And these are the last 2 metrics that we care about. In the signal energy, we will square each value and each sample and sum them up. And it's just a simple measure of the overall electric activity in the beat. And the baseline will be the mean of the first 20 samples, as you can see here. Again, we use this measure to know how much signals has shifted. So again, these are just real clinical metrics. You really don't have to know all the technicality about it, just what we need about it mathematically. Then moving on to section 5, here are the readings that we got from the selected one right now. And then in section 5, we put it all together. So what happens here is we get Gemini to interpret those metrics that we extracted. So you can see here, we're using the function build prompt. Now, this part is really important because it really puts together what you actually want from the model. So we will tell Gemini, you are a clinical ECG analysis assistant, and we will tell it exactly what we want from it and what we were giving it. So we're telling it that we're giving it a data set, and then we will give it the futures. So this text here, over here, it's the entire string. It's the engineering, basically. The way you phrase this, what you ask for, the structure of the output, that's what you're designing. So changing this prompt would change everything, and it's really important. So here again, for the technicality of it, we will use get Gemini interpretations, and this will call the Gemini API. And again, using the Gemini generative AI SDK, and we pass this model name and the prompt, and we will get back a response, as you can see here. So this is just a plain language interpretation. It will interpret the reading you gave it, and then it will compare it to the expected values. So you can see here, for example, it diagnosed, it was telling you the QRS width of 64 milliseconds. It's excellent. It's falling perfectly within the range, and so on. It will do this for every reading you give it. And then one key limitation, it will give you a one key limitation of the future extraction approach. See, here it's for normal beat, and here it's for the ventricle ectopic beat. In section 6, it's where we will experiment, and you will experiment with me once we're done. What we will do here is we will play around with the dataset. Now, we just use the default, but now here we can change it to normal beats or keep it as ventricle beats, and just, the classes. But then we have the indexes, we can change it. For example, number 6 is just the 6th patient, but we can put it back to 1, we can put it back to any number we wish. And that's it for this part. Let me know if you have any questions so far, and if not, we can start experimenting with it.
All good.
Okay. So here, we can change this to normal beats. Let me show you the normal beats first. So for example, let's pick the 3rd index, and let's run it again. So here we get a ECG reading, and here are the extracted values. So the R peak, the QRS width, the rise time, everything. And then what's the verdict from Gemini. So the plain language interpretation here, it's going to tell us that what the futures really describe. So it's going to describe the R peak, it's going to describe the QRS width, and tell us exactly what those futures really tell us. And then, depending on the interpretation, how these futures compare to what you would expect for this beat type. So what we're expecting here is a normal beat. So what happens here for a normal beat, an R peak amplitude of 1 and a QRS width of 56 milliseconds are generally consistent with expected values. So here it's basically diagnosing, are the readings we get are what we would usually expect with a normal beat or not? And it will give you like a range, and why does it make sense? See here, for example, it's telling you, however, a rise time of 0 is physically impossible for a real biological signal and strongly suggests an error in future extraction or calculation. So it will even criticize what the readings gave us. And then we asked it also to give us a key limitation of this future. So here it says that the limitation is automated futures extraction can sometimes yield a non-physiological or values like the rise time. So this could be an issue with the signal quality and the algorithm. So this is basically, for example, an example of the normal beat. Now let's go back and change it to ventricular beats. And now let's pick a index of, for example, 6. Now we got a reading, again, with the features we need and the interpretation. So again, the plain language interpretation, it's telling us that the numbers describe specific characteristics of, okay, the R peak, it's, okay, again here, it's just explaining what the features are and what they will represent and what we need from them. But what we care about is the comparison. So for a ventricular ectopic beat, we typically expect a significantly wider and often bizarre QRS complex. Yeah, so now it's reading what we gave it and it's giving us a verdict. And due to the comparison, it's telling us that it works with the, it's consistent with what we expect from a ectopic beat. And again, it will give us a limitation. So it's saying analyzing a single segment. Yeah, so again, it's criticizing the readings and giving us a limitation of it. Any questions so far? Did anyone employ it and get any errors or anything? Please type in the chat or just react with a thumbs up. Okay. So I will show you okay. So one last thing is this is just a prototype or just a rough code that we just care about the output. But what if you want to deploy this into a real thing or you want to publish it? So I will show you a live deployment of this. So this is a web app. It's running on Google Cloud Run. So this is a serverless hosting platform, and anyone with this URL can open it right now. But because we're limited to the credits and all, so I will just be showing you how it works. So let's say we want to check the normal sinus rhythm, and let's pick an index 2. Again, an index is just the patient number. And then we will press on Analyze Beat. Now this is running locally here, so it might take a bit of time. Yeah. So here again, this is basically what I just showed you in the collab, but it's looking more, put together and something you can deploy, something you can, rely on. And again, it's just the same thing again. We're getting the plain language interpretation, the comparison, and the key limitation. Again, let's try with the ectopic beat, and let's pick an index of 5, let's say. Again, we got the result of an ECG reading with the extracted features and the verdict from Gemini interpretation. That's basically what the hands-on experience for today is. So please let me know if you've faced any errors, any questions you might have, any part you're stuck on, please let me know. You're welcome to open your mics and ask and discuss.
Hi, Hanan. You had a great explanation. Thank you so much. But I do have a question.
Yes, go ahead.
Yeah, how is this different from just asking ChatGPT to describe an ECG?
So basically, if we just go to ChatGPT and ask it about the ectopic beat, for example, it's gonna give you a generic answer. It's not gonna give you something specified. But here it gives you something more curated to the patient itself. Because not all ectopic beats or not all disorders would look the same on an ECG reading. So when we put it through this pipeline, it will give you something more curated and more detailed. Like as you can see here, when we were experimenting with here in section 6, yeah, as you can see here, it was giving you the like an explanation what should happen usually in an ectopic beat and what do the futures usually would look like. And also it gave you the matching of the readings to what we expect here. But also it gave you a limitation. Why could it be wrong? Why does it not make sense in this one certain metric? So that's the main difference. ChatGPT would just give you a generic answer and it would not pay attention to the details of the patient's reading itself.
Okay, makes sense. Thank you so much.
You're welcome. Any other questions? Oh, there's a question in the chat. Yes, typically because in the biomedical field, especially biomedical engineering, what we do is we try to make it more personalized for the needs of the patient. We can't just have one size fits all. And this is why we really need those pipelines and we need to utilize those models better than just having one verdict for all patients and all types of disorders. Thank you, Jenna, for your question. Any other questions, guys? All right. Thank you guys so much for your time and thank you for being here. I hope you had, enrichment and explored new fields and a new field in biomedical. As I can see, most of you guys are doing computer and cyber. So I hope this was fun for you as it was fun for me. And yeah, have a nice rest of your evening and thank you so much.